Okay, welcome to Lesson 6 of Module 5. The title of this lesson is Graphs of Linear Functions and Rates of Change. So we are going to use what we know about rate of change to determine what the graph of a function would look like, specifically to determine if it will be linear or not. Let's just look at the opening exercise. You have this in your notes. Here are three functions, the input-output tables for three functions, and you're asked to look at them and decide if they are linear or not, if they would graph as a linear function, and to justify your claim. So I'm going to give you I would ask you to take just a few minutes to do that. Don't spend too long on it, because after we have a discussion about it, we're going to come back to this exercise with maybe a few more tools to evaluate whether these will be linear or not. But use what you know and see what you can do with that. So you can go ahead and pause the video now and do that, and then come back and we'll continue our discussion. Okay, so in lesson 5, we talked about how the graph of a linear function, or the graph of a function, will be identical to the graph of the equation that describes that function. So we saw some linear and nonlinear examples of that. And so today we're going to be looking at these input-output tables. So here's one that we're going to work on together. We have 4 input-output pairs. We could graph these and see if they look like they're in a line, but we want to be a little more precise than that, although the graph could give us a good starting point just by plotting these points. But we are going to look at use what we know about linear equations, and we're going to see if we can determine the rate of change between these points. So if I can find the slope, or the rate of change between points in this table, and all of the slopes are the same rate of change between every point, then I would know that I had these points lying in a line. So remember when we had slope, when we had when we had xy pairs, and we could have x1, y1, and x2, y2. These would be 2 separate points on a graph. We could find the slope by looking at the difference in the y's divided by the difference in the x. Okay, so in this case we have input and output. And we can look at 2 of those, and to distinguish them we'll put 1s for the first point and 2s for the second point, just like we've done. So we've got pretty much the same situation. So we're going to use, and this is slope obviously, so we're going to use the same formula. We're going to look at the difference in the outputs. Let's abbreviate that. Output 1 minus output 2 over input 1 minus input 2. So for a function, for points on a function, it's the exact same process as points on ordered pairs on a grid. Okay, so let's try it for the first pair of points on our graph. So we have the ordered pair 2, 5, and the ordered pair 3.58. So those are inputs with their corresponding outputs. And so if we want to find the difference, the slope between these 2 points, we would have 5 minus 8 divided by 2 minus 3.5. So that would be negative 3 over negative 1.5. And that would give us a positive number because a negative divided by a negative is positive. 3 divided by 1.5, I hope you'll recognize that as 2. If not, you could multiply through. But 1.5 is half of 3, so that fraction is equal to 2. So the slope between those 2 points is 2. So now what I want to do is I want to do the slope between the second and the third. And I'm going to compare that. So let's look at this. So I won't write the ordered pairs out, but the slope is going to be the difference in the output, or the y. And so I'll say 8 minus 9 over the difference in the input, 3.5 minus 4. In this case, I've got negative 1 over negative 0.5, or negative 1/2, which is also equal to 2. Okay, so we have a constant slope between 2 pairs of points. So let's see if this next pair fit in with the pattern. Okay, so my slope is equal to, and remember, I can do these in any order I want. So just because we're calling one point the first point and the second point, I can subtract in a way that's convenient for me. So for this last one, let's do it different. I'm going to do that the slope is 10 minus 9 over 4.5 minus 4. The important thing when doing this is that whichever point, this was the y-coordinate. Okay, so we did 10 and then 9, so I have to do the corresponding subtraction in the same direction, 4.5 minus 4. And so for this calculation, I'm going to get 1, and once again, 4.5 minus 4 is 0.5. They're both positive differences, and it results in a 2. Okay, so we've got some strong conclusions here that this might be a line. And actually, that is all I need to check. Let's think about this. We've got 4 points, 2, 3, 4. And let's not draw the first 2. Let's only draw the first 2 rather. So let me get a different color for this. Okay, so we calculate the slope between these 2 points and find that it's a given value. And so then I put in another point. Okay, so if this was our first point, our second point, we have our first point, second point, third, and fourth. Put in the second point. Now I'm putting in a third point, and I calculate the slope between the second and the third, and if it comes out the same, here, you could think about, what can I conclude about the slope between the third and the first? Do I need to check it? if these two, between 1 and 2, is equal to the slope between 2 and 3, do I need to check the slope between 3 and 1? It turns out that I don't, because I have these similar triangles going on, and I can see by this that they would all be the same slope. Okay, let's go on. So then if I add a fourth point and find that its slope between 3 and there is the same, then I would know that all 4 of those points are in the same line. Okay, what you don't want to do is this. If I check, okay, let's get rid of this. If I just check them in pairs, let's look at what could happen. I've got this. If I check 1 and 2, and they have the same slope, and then I check 3 and 4, and they have the same slope, I don't necessarily know that they're on the same line because they could be on parallel lines. And that's why I have to check the points. I have to check them in pairs like that. And until you get comfortable with this, you can check every pair of points if you'd like for slope, and just to make sure that they're all so I could check the slope between the first point and the fourth point. Let's do that. We would have that the slope is equal to 10 minus 5 over 4.5 minus 2, and so the slope would be 5 over 4.5 minus 2 would be 2.5, and that is a slope of 2. Okay, so the rate of change, or the slope, between all the pairs of points is 2, so we know that this is a linear function. So what I know now is that the slope is 2 between all the pairs of points in this input-output table. So I know that I'm going to have a situation where y is equal to 2 times x plus b. Because remember, every linear equation can be written in the form, this slope-intercept form, where the slope is the coefficient of x, and we have a constant b that's the y-intercept, and then we have our variables x and y. So we did this back in Module 4, and we can solve for b by putting in one of our input-output pairs. Okay, so I can choose the point 2, 5 to check, or not to check, but to put into this equation. And so I would replace y with 5. Then I would replace x with 2. And leave b alone, so I can solve for b. So I have 5 is equal to 4 plus b. Subtracting 4, I get that b equals 1. So the equation of this input-output function here is y is equal to 2x plus 1. That's the rule here. So this is a little like the game that we played in class last week, where I had you trying to guess the rule, and somebody said, but is there a way that we could just come up with it? And here's the way. So let's look at this. So make sure all of our points check out. So 2 times 2 plus 1 is 5. 3.5 times 2 is 7, plus 1 is 8. 4 times 2 is 8, plus 1 is 9. 2 times 9 is 9. 2 times 4.5 is 9, plus 1 is 10. Okay, so our rule is 2x plus 1. And you might have already seen that, but we did it algebraically. We reasoned through it. Okay, so we found the function rule for this input-output table, and it's a linear equation that's going to have the same graph as the function itself. And if we did put it on a graph, it would be a line. It would look like a line because we went through quite a bit of in-depth learning about this y equals mx plus b form and how it always graphs as a line. Okay, let's look at another one. Now here's another table, input-output table. The following table represents the outputs that a function would assign to given inputs. We want to know if the function is a linear function, and if so, what linear equation describes the function. So we could begin by looking at pairs of input-output corresponding outputs and calculate the slope between them. Okay, so we could say, get white here. So if I pick the first two, I would have that m equals 9 minus 4. So the difference in, so I'm looking at these first 2 points here. So 9 minus 4 over 3 minus negative 2. 3 minus negative 2. And that slope is 5 over 5, which is equal to 1. So we've checked these first 2 points here. Okay, so the slope is 1 between those two. So let's keep going. And for the second pair of points, I have to keep changing colors here. We're going to use those two right there. And so I'll have 20 20.25, 20 and 25 hundredths minus 9 over 4.5 minus 3. Okay, so let's double check what we've done. I did 20.5, 20 and 25 hundredths minus 9, and over 4.5 minus 3. Okay, so I got everything in the right order. And I can just do the math here. So this would be 11.25 divided by 1.5, and so I can come over here and do that. Move down. Okay, so that division brings us to 7.5. It's certainly not 1. So right off the bat right now, I know this is not a linear equation. But I could check one more pair of points. Let's see what this one is. 25 minus 9. I'm going to use this last point the fourth point and the second point. So 25 minus 9 over 5 minus 3. So 25 minus 9 is 16. And 5 minus 3 is 2. So the slope here is 8. Okay, so the slope between those 2 points is 8. I've got 8, a 7.5, and a 1. So what I know is there's not a constant rate of change between these inputs and outputs. And so this would not be a linear function. Because if it were, it would be the same. Okay, so you might have guessed what this function is. I know that for 3 of the points, it works to multiply the number by itself. Negative 2 times negative 2 is 4. 3 times 3 is 9. 5 times 5 is 25. And I'm assuming that 4.5 times 4.5 is 20.25. You could check that out later. But that's not a linear rule. That is x squared for the output. X for the input, x squared for the output. So not a linear rule when there's an exponent like that. So we've shown that by calculating the slopes of these pairs of points and showing that they're not equal. So we've got plenty of evidence to show that, and and that's pretty much it. That's how you're going to determine these equations. If it's nonlinear, you won't need to find an equation that describes the function. And if it's linear, you can use this method of once you find the slope, use it in the y equals mx plus b equation and solve for b. And then it's a good idea to then check your inputs and outputs. Okay, so let's go back to the opening exercise and use what we know on these problems. And probably you should pause the video and try a couple of these yourself. I'll do some over here. So I'm going to calculate some of these differences. So we'll do these two first. So I'm going to do 7 minus 5 over 4 minus 2. And I can see that that's 1. So let's do this, the next 2 points, number 2 and 3. So we have 8 minus 7 over 5 minus 4, which gives us 1 again. And then I'd have, checking the last two, I'd have 11 minus 8, which is 3, over 8 minus 5, which is 3, so that's 1. So this would be a linear function. Okay, and let's see if we can determine the rule real quick here for this first one, because we've determined that the rate of change between every pair of points is 1. And so we should be able to find an equation. If x is the input and the output is y, then we have y equals mx, and the slope is 1, so it's going to be y equals x plus b. And we can see right off the bat that if we plugged pairs of points in here, y equals x plus 3 is what would work. So you just take this function rule is take the input and add 3 to get the output. Okay, and that's a linear rule. All right, let's look at the next ones. We've got 2, 4, 3, 9, 4, 16, and 5, 25. And hopefully you're already noticing that this is not going to be a linear equation. So 9 minus 4 is, I don't have a lot of room to do this, so I'm going to do it up above. I've got 9 minus 4 over 3 minus 2. So that would be 5 over 1, or 5. So the slope between the first two is 5. The slope between the next two, 16 minus 9 is 7. Do it over here. 16 minus 9. And so if I do 16 minus 9, that would be 4 minus 3 over here. Over 4 minus 3, which is 1. That does not look good. Sorry. Got to get rid of this. 16 minus 9 divided by 4 minus 3 is equal to 7 over 1, or 7. Okay, so we can see our slope is increasing, and if we do one more, we'd have 25 minus 16 over 1 again, 5 minus 4. So 25 minus 16 is 9. And so we can see we don't have a consistent rate of change or slope. So this one is not linear. Okay, one more. Give myself some room here. Okay, so if I check the first pair here, I'm going to get 1 minus negative 3, the difference in the y's, or the difference in the output, over 1 minus 0. So the change in the input is 1. The change in the output is 4, right? Because 1 minus a negative 3 is 1 plus 3, which is 4, over 1, which is equal to 4. All right, let's check the next 2 points. I've got 1 and 6. So the difference in the y is 6 minus 1. The difference in the x is 2 minus 1. So that would be 6 divided by 2. Or no, I'm sorry, it would be 5 divided by 1, which would be 5. Okay, so I've got a slope of 5 and a slope of 4. So I already know it's not linear. We'll check another one here. 9 minus 6. So I'm going to do these, the fourth and the third now. 9 minus 6 over 3 minus 2. So that would be 3 over 1, or just equal to 3. Okay, so this one would also be not linear. Okay. Okay, so we've got an exercise that we can do, and let's just walk through it. And if you're feeling confident, you can pause and work on it yourself, and then just come back and check your work. Okay, it says a function assigns inputs and corresponding outputs in the table below. Is the function linear? Check at least 3 pairs of inputs and their corresponding outputs. So I'm just going to choose that pair, and that pair. So I've got 2 minus negative 1 over 1 minus 2. So this becomes 3, and the denominator is negative 2. So we've got negative 3 halves. Okay, so I'm making all kinds of mistakes today. And these are easy mistakes to make. 1 minus 2 is negative 1, because it's 1 plus a negative 2. So this slope here would be negative 3. Okay, easy to make these mistakes. All right, so let's check another pair of points. We'll check the next pair. We've got negative 7 minus negative 1. Then on the bottom, got to go in the same order again, would be 4 minus 2. Okay, so negative 7 minus negative 1, this becomes plus positive 1. And so negative 7 plus 1 is negative 6. 4 minus 2 is positive 2. So this becomes negative 3. Okay, I've checked out 2 pairs, and they both have the slope of negative 3. So let's do the last pair. We'll do 3 and 4. So I'll have negative 13 minus negative 7 over 6 minus 4. So the difference between negative 13 and negative 7 is negative 6, because this will become plus 7. So negative 6 over 6 minus 4, which is 2, we get negative 3. So this function is a linear function because it has a constant rate of change. Okay, what equation describes the function? Well, we had a slope of negative 3, so we can start with that. And remember that every linear equation can be written in this form. So y is equal to negative 3x plus b. So our job is to find out what that constant is. So I'm going to use the first input-output pair because it's the smallest numbers, 1 and 2. Let's go back. So I'm going to take the first pair on the table, which is 1, 2, and I'm going to insert it into this equation. So y is 2, so I have 2 is equal to negative 3. X is 1, right here, so it goes in for x. 3 times 1 plus b. So if I add 3 to both sides, I'm going to get that 5 is equal to b. So the graph of my function would be y equals negative 3x plus 5. Okay. What will the graph of this function look like? Well, it will be a line. So further explanation would be the points have a constant rate of change. And I know that y equals mx plus b graphs as a line. So anytime I could put it in that form, I know it's going to be a line. Okay, so here's the summary. When the rate of change is constant for pairs of inputs and their corresponding outputs, the function is a linear function. And we already knew we could write linear equations in the form of y equals mx plus b to express a linear function. And from the last lesson, we know that the graph of a function is the same as the graph of the equation that describes it. So remember, there was a good example of that in the last. We knew that the area is the side length squared for a square. And so if area is our output and the S, the length of the square, was our input, then we would have a situation where we have ordered pairs that are input and input squared, or S and S squared, which is the area. Input, output. And so we could see that this was going to be the same as y equals x squared, where the input is x and the output is y equal to x squared. So so that was what we learned in the last lesson, and we know that for these linear functions, just remember that you can always use y equals mx plus b to write an equation for those. Okay, so good luck on the assignment. That was it's a little bit shorter and to the point, and we'll see you for lesson 7.